Hello everyone, this is Professor Keen. We have been talking about Galileo's dialogues concerning two new sciences. You might remember that these two new sciences that Galileo is discussing are, first of all, the strength of materials, and secondly, projectile motion, which we haven't really gotten to at all yet. In the last several lectures, we have gone through chapters 1 through 5 of A Student's Guide to the Great Physics texts, which is basically comprises the first day of Galileo's dialogues. Remember, this book is divided into 4 days of dialogues between Salviati, who represents Galileo's opinions, and Sagredo and Simplicio, who then question Salviati and kind of tease out the meaning of what Salviati is suggesting. So in the dialogues, the first day began with a discussion of what it is that makes certain materials stronger or harder to break than other materials. And Salviati, Sagredo, and Simplicio began this discussion, but in the course of the discussion, there were many digressions, and these digressions covered topics like nature's abhorrence of a vacuum. That was provided as one explanation why certain things stick together or are hard to break. And then we got diverted a bit into the idea of motion in a vacuum and falling objects. How would an object fall in a vacuum as opposed to different kinds of media? And then we even got into some digressions about pendular motion and harmony and music theory. We're going to come back to the topic of falling bodies, but in the meantime, what happens at the beginning of day 2 of the dialogues is Salviati, Sagredo, and Simplicio come back to talking more directly about the cohesion of substances and the strength of materials. And they're specifically going to be talking about it in the context of how hard it is to break a beam. So in this lecture, we're going to start talking about beam breaking. Again, this is in chapter 6 of A Student's Guide. But before we do that, I want to make one further digression about Galileo's use of mathematics, in particular how he writes formulas. So I'm going to cut my webcam here, go to my sketchbook. This is an aside on Galileo's use of proportions. Galileo's use of proportions. You probably noticed in the course of reading Galileo so far that it's very seldom, in fact, he never writes formulas in the way that we write formulas. So for example, if we wanted to nowadays write an equation for the mass of an object, we would write mass equals the density of the substance out of which it was made multiplied by the volume. This is kind of the contemporary way we do this algebraically. Galileo does not write formulas like this. Instead, what he does is he always compares like quantities. So for example, if we wanted to know the mass of an object compared to another object, we would say, well, the mass of object 1 is to the mass of object 2 in the same ratio as the density of object 1 is to the density of object 2, compounded with, this is how Galileo would do it, compounded with the volume of object 1 compared to the volume of object 2. Notice what Galileo is doing here, he's always comparing like quantities. He's saying if you want to know how big one object, how massive one object is compared to another, you have to compare their densities and compound that with a comparison of their volumes. The reason he does this is because then he is always comparing like quantities, and he's always multiplying dimensionless quantities, right? And the reason he does this is somewhat for philosophical reasons and somewhat for historical reasons. When you want to compare one mass to another, that makes sense. You can put it on a balance and say, how big is this mass compared to this mass? If you want to compare the densities of an object, of two objects, those densities are like quantities, and likewise volumes are like quantities. And notice when you form these ratios, all of these things are then dimensionless. When you compare two masses, and you find a ratio, you'll get a 2-to-1 ratio, or a 5-to-1 ratio, or a 3-to-4 ratio. So this would be a dimensionless quantity, and then you're multiplying all dimensionless quantities here. You don't run into this strange situation where you're multiplying unlike quantities. That was, I think this comes from ancient Greek mathematics, where everything is given a geometrical interpretation. You're not multiplying velocity times time. You're not multiplying distance. You're not dividing distance by time. You're always comparing like quantities. After all, what does it mean to divide distance by time? It's like comparing apples to oranges. So Galileo is thinking about this in a particular way. I know it's perhaps a little bit unusual to you, but I think there's a certain internal logic to it that you can appreciate it if you think about why he's doing that. Okay, so that's a digression on Galileo's use of proportions. All right, now let's come back and talk about the coherence of substances, which we went far afield from. Whatever the cause of coherence or cohesion, it is apparent that some substances are harder to break than others. Some substances are harder to break than others. And this can be due to a number of reasons. So let's ask why this is. So why is it that some substances are harder to break than others? Well, first of all, it might be due to the type of material out of which they are made. Right? So even if you have two beams that are otherwise identical, but one is made of wood and the other one is made of steel, the steel one is going to be harder to break, all other things being equal. So the type of material is one reason why certain things are harder to break than others. A second reason is because the shape of the object might make one harder to break than the other. So, for example, if you had a sphere of wood, it would be harder to break than a thin stick of wood. So the shape of the material comes into its robustness. And third is how you try to break it. So certain ways of breaking things are are easier or more efficient in breaking them than in other ways. And there are two ways of breaking things that Galileo specifically focuses on, and I'd like to highlight these right now. So how to break objects, first of all, you can apply a longitudinal force in order to break it. So that would be, imagine you have a wall, and sticking out of the wall is a cylindrical rod made of some material that you're going to try to break. So this is kind of wedged into the wall like this. Maybe this is a block or something and it's sticking out of the block. A longitudinal force would be if you grab the end and you pull straight out and you try to break it like this. That would be a longitudinal force. And this way is fairly hard to break something. The other way that Galileo considers is a transverse force. Okay, so imagine the same rod sticking out of the same wall. Try to draw the same rod here. It's exactly the same, but instead of pulling straight outward, you bend it downward like that. This would be a transverse force. And as you might imagine, this kind of force is going to make it easier to break the object. It's easier to break it downward like this than pulling it straight apart. Okay? And the question is, so this might be intuitively obvious to you, but this raises the question immediately, why is this? Why is it easier to break something using a transverse force compared to a longitudinal force? Even if these are the exact same forces, maybe a 10-pound force, this one might cause it to crack, and this one would not cause it to crack. So why is it easier to break in one way or the other? This, by the way, is something that Galileo asks on page 72 of the text. And in order to answer this question, we have to understand something called the law of the lever. We must understand the law of the lever. Okay. And the law of the lever, I'll just state what it is right now, and then we're going to have to demonstrate the law of the lever, and then come back and apply it to these two situations to see why it's easier to break in one case than the other. So let me just quote what Galileo says, that so for the law of the lever states that for a bar on a fulcrum, let's suppose you have a fulcrum like a balance point, and you put a bar across it, the force, he says, bears to the resistance the inverse ratio of the distances which separate the fulcrum from the force and the resistance. Okay, that's kind of a mouthful, but what he's essentially saying is that if you have a balance and you want to suspend weights from both sides of the balance, the force that you hang on one side compared to the force you hang on the other side have to have a certain ratio to one another that depends on how far you hang them from the fulcrum, okay? And what I'll do is I will pick up at this point when I do my next lecture. So I'll stop right here and come back to this.